is the notes for AP Calculus on the topic of integration by parts. So this is a method of integration that really comes from the product rule for differentiation. So let's review that real quick. So if we have the derivative of f of x times g of x, that would require using the product rule, where f of x is our first function and g of x is our second function. So remember the pattern for that. You would take the derivative of the first function, so the derivative of f of x is f prime of x, times the second one as it is, g of x, and then plus the first one as it is, f of x, times the derivative of the second one, g prime of x. So after you use the product rule, what we can do is if we first, we're going to integrate both sides of the equation. Before we can do that, we really need to multiply everything by dx. The variable of integration here. So if we multiply all these by dx, then that allows us to integrate both sides of the equation. And since these are added together, you can integrate each one separately. So look at what we have over here. Similar to the second fundamental theorem of calculus, except without the lower and upper limits, we've got the integral of a derivative. So since those are reverse operations, they essentially cancel each other out. And all we're left with here is f of x times g of x. And these, in this form, we can't really integrate without knowing specifically what they are. So we'll just leave it in general form, f prime of x times g of x dx plus the integral of f of x times g prime of x. So the way we get our formula for integration by parts is by actually trying to solve for this f of x g prime of x. The way we isolate that is by subtracting the integral of f prime of x g of x from both sides of the equation. And when we do that, we'll have this integral by itself. Let me switch into the left side of the equation here. So the integral of f of x g prime of x dx equals f of x times g of x minus the integral of f prime of x g of x. So initially this may not seem like it's making it simpler but more complicated, but the idea with integration by parts is to take this integral here, and if we choose f and g prime properly, we should be able to make this integral simpler so we can actually integrate with f prime and g of x. So let's look at some example problems now. Now, as you get better at this, you'll get better at deciding which part of the integral to set equal to f of x and which part to set equal to g prime of x. But kind of the general rule is, since we want to make it a simpler integral, we let f of x equal the part that has the simpler derivative or simplifies better through differentiation. And we let g prime of x equal the part of the integrand that can be integrated more easily or that doesn't get at least more complicated by integrating. So let's take a look at this first one here. We've got x and cosine of 3x multiplied together. So you can't integrate in this form. If you tried using u substitution, said u equal to 3x, we'd still end up with this x left over here. So you couldn't get it all in terms of u. So this is one we can use integration by parts. And the way to decide is, well, which one is going to get simpler if we take the derivative? And that's going to be x rather than cosine of 3x. Cosine of 3x doesn't really get more complicated, but it doesn't get simpler either. So it's better to choose f of x to be x and g prime of x to be cosine of 3x. So then we can take the derivative. Notice what we need is the derivative of f of x and g of x. So if you take the derivative f prime of x, well, the derivative of x is just 1. And then in order to get g of x, we're going to need to integrate this. Now technically we would need dx's on both sides, but just for time's sake, what we're doing is integrating both sides of that. And that would give you back, when you integrate g prime of x, that gives you back g of x. So you're finding the antiderivative here. And technically, you normally have to use u substitution on this, saying u equal to 3x. But recall the shortcut for integration, if the derivative is just a constant, in this case, what he said u equal to, the derivative of 3x would just be 3. you can essentially just divide by that constant, and then you don't have to use substitution at all. So in this case, since the derivative is 3, we divide by 3, which is like multiplying by 1/3. And then the derivative of cosine, so the antiderivative of cosine is sine. So now we have everything we need. We have f prime and g of x, and so now we can split this up. So this integral equals f of x, which we said equal x, times g of x, which we just found was 1/3 sine of 3x, and then minus, right there, integral of f prime of x, which was just 1, times g of x, again, which was 1/3 sine of 3x, and then times dx. So you can see, by using integration by parts, this integral now is simpler than the one we started with, because there's no longer an x there. So let's just simplify what we've got here. So here if we simplify this, pull the 1/3 out in front, that's going to be 1/3 x. I'll just box this part out to keep it kind of separated. 1/3 x times sine of 3x. And minus, we can pull out of here the constant of 1/3. And then all that's left in our integral is sine of 3x dx. And now we can actually integrate that. So leave the 1/3 x sine of 3x here. Oh, I forgot to point out, normally on these indefinite integrals you would put a plus c here. But in this case, since we're not quite done with it yet, that plus c we'll just put at the very end once we've integrated it completely. We don't need more than one unknown constant there. So we got the negative 1/3 out in front. And then, similar to how when we integrated or found the antiderivative of cosine of 3x, you would technically use u substitution here, set u equal to 3x. But since the derivative of 3x is just a constant, you can easily just avoid u substitution and just multiply by the reciprocal or divide by that constant. Divide by 3 is multiplied by 1/3. And then when you integrate sine, that gives you negative cosine. And then that's when you can put the plus c over again. Oops. Forgot to put it there. And if we just simplify that now, so we'll have 1/3 x sine of 3x. Multiply the constant, the 1/3 times 1/3 is 1/9, and then negatives cancel out, so it becomes a positive 1/9. And then cosine of 3x plus c. So that would be our answer for what this integral of x cosine of 3x equals using integration by parts. All right, let's take a look at another example. Yeah, I just put the formula at the top here so we can keep referring to it as we go through these examples. So the next one, we've got the natural log of x dx. So we want to figure out again what we set part of the integral equal to f of x and part of the integral equal to g prime of x. So f of x on this one, and then g prime of x. But sometimes you may have an integral like this where it appears there's only one thing inside it. So you just have to think about, well, is it easier to take the derivative of natural log of x or integrate? Well, if it was easier to integrate it, we wouldn't even need integration by parts. We could just tell what this is. So it's easier to take the derivative, so that's your clue you'd want to set it equal to f of x, because that's the one we're going to take the derivative of. And if that's all there is, then g prime of x, but let's just be a 1. 1 times natural log of x is just natural log of x. So if there's nothing left to set it equal to, it's just 1. And now let's take the derivative of each of these. Sorry, the derivative of the first one. So the derivative of f of x, f prime of x, derivative of natural log of x is 1 over x. And when you integrate or find the antiderivative of g prime of x to get g of x, we integrate that or find the antiderivative of 1 is just x. And again, we don't have to put the plus c until the end. So now we have everything we need to split this up here. So this integral equals f of x, which is natural log of x, times g of x, which is x. minus integral of f prime of x, which is 1 over x, times g of x, which is x, and then times dx. So if we can simplify that, bring that x out in front. Notice this is not inside the natural log, so it can't become x squared there. Just x out in front, and then natural log of x minus, notice what simplifies here are the x's reduced out. So all that's left inside of our integral is just 1 dx. It doesn't get much simpler than that there. Integrate. So we just leave the x natural log of x out in front. Minus, when you integrate 1, you just get x, and then you put plus c. So that's what the integral of natural log of x equals using integration by parts. All right, let's take a look at another example. It's a little bit more difficult. So again, this one, we've got x squared and sine x. So we have to decide which part of that to set equal to f of x, and which part of that to set equal to g prime of x. So we set f of x equal to sine x, the derivative of that is cosine. Well, that doesn't really make it any simpler. But if we set f of x equal to x squared, the derivative of that is 2x, so that does get a little bit simpler because the exponent reduces by 1. So that's how you kind of decide that it's probably better off setting f of x equal to x squared and g prime of x equal to sine of x. Again, let's take the derivative of f of x, f prime of x, with the derivative of x squared would be 2x. And let's find the antiderivative, or integrate g prime of x to get g of x. When you integrate sine, that gives you negative cosine. Alright, so that means this integral again would equal f of x, which is x squared, times g of x, which is negative cosine x, minus integral of f prime of x, which is 2x, times g of x, which is negative cosine x. So the way I remember where things go, without having to refer to the formula every single time, is the first ones are just the functions, original functions, f of x times g of x, and then it's minus the other ones that go inside the integral are the ones we found here, both f prime and g of x, not the ones we started with. And remembering it comes from the product rule can make it easier to remember that as well, I think. So let's go ahead and simplify this. Pull out the negative out in front. X squared cosine x. And you can pull out a negative along with the 2 times the negative that's already out there, makes it a positive 2 up front. Integral, we still have x and cosine x over there. So this integral is a little bit simpler than we started with. It's x cosine x rather than x squared sine x. However, it's not one we can just integrate right away because of that x in there. If it was just cosine x, we could if it was just x. So sometimes what that requires is that you use integration by parts more than once. So we repeat the same process on this integral x cosine of x. So again, we have to decide what part to set equal to f of x and what part to set equal to g prime of x. So the one that would simplify more by taking the derivative is x. And then cosine doesn't really get more complicated when you integrate, so we set g prime equal to cosine x. So then take the derivative. F prime of x, the derivative of x is just 1. And when you integrate, you'll find the antiderivative of cosine x, which is sine x. So we'll have this negative x squared cosine x out in front. But what you have to be careful of is we're using integration by parts on this integral x cosine x, but notice there's a 2 out in front. So whatever that coefficient is, in this case positive 2, put an open parentheses, is going to get multiplied by the whole thing. We use integration by parts here. So we'll have f of x times g of x, so that's x times sine x minus the integral of f prime of x, which is 1, times g of x, which is sine x dx. And now we finally have an integral that we can integrate as sine of x equals some point. So theoretically, you can actually use integration by parts more than twice. Use it 3 times or 4 times. So if we start with x to the 9th here, instead of x squared, you can see we have to end up using integration by parts 9 times, but generally won't see too many of those because they just really take a long time to work out. So negative x squared cosine x, and distribute out the 2 there. They become 2x sine of x. And here, when you integrate cosine, you get negative cosine. But there's a negative and a 2 that we distribute out in front. So initially you'd have a negative 2 there. But when you integrate sine, it's negative cosine, that changes that to be a positive 2. And then you can put the plus 2 for that. So that would be the answer for what the integral of x squared sine of x. Using integration by parts twice. Okay, let's look at another example, another indefinite integral, where something a little bit different happens. On this one, we have e to the x times cosine x. It's a little bit tough to tell what does that equal to f of x and what does that equal to g prime of x. Because neither one really simplifies when you take the derivative, and neither one really gets more complicated when you integrate. So it might work both ways, but I know it works this way. So you set f of x equal to e to the x and g prime of x. Be consistent with my colors here. So I set g prime of x equal to cosine x. And then when we take the derivative, f prime of x, the derivative of e to the x, remember that's the one that stays the same, is just e to the x. And when you integrate or find the antiderivative of cosine x, that's just sine of x. So we'll have f of x, which is e to the x, times g of x, which is sine x, minus the integral of f prime of x, which is e to the x, times g of x, which is cosine x. So again, we can see, well, e to the x cosine x, it didn't get simpler, but, oops, sorry, that's not cosine x, that should be sine x, g of x. Actually, I put g prime in there. So the integral didn't get simpler, but it didn't get more complicated. So let's see what happens if we try to use integration by parts again here on this one. So again, if we set f of x equal to e to the x and g prime of x equal to sine x. Well, then the derivative f prime of x with e to the x again is just e to the x. And when you find the antiderivative, we'll integrate sine x, that gives you negative cosine x. So I just bring down this e to the x sine x minus, this time, instead of having a 2 out in front, when using integration by parts again, that negative 1 is going to get applied to the whole thing when we use integration by parts there. So we'll have f of x e to the x times g of x negative cosine x minus the integral of prime of x e to the x times g prime of x, sorry, g of x negative cosine x. Now let's go ahead and just simplify this a bit. So we got e to the x sine x. If we distribute the negative, there's already a negative, that's going to make it plus e to the x cosine x. And then the negatives cancel out there, making it plus integral e to the x cosine x dx. So if we notice what we've got here, this integral e to the x cosine x dx, that's what we started with. So you can see if you kept trying to apply integration by parts, we're going to end up in this loop, right? Well, if we tried it again, we'd end up with an integral e to the x sine of x. Try it again, we get back to e to the x cosine x. So you might think, well, this is impossible because we have to do this forever, we never get to our answer. However, there's one simple, but maybe not obvious trick we can use here to help us solve this. So remember, this whole thing equals our integral that we started with, right? E to the x cosine x dx. So if we want to solve for that integral e to the x cosine x, oops, I just realized we made a mistake. These negatives canceled out here on this integral. However, what I forgot is to distribute the negative on the outside. So this should actually be a minus. Not a plus, sorry about that. Okay, so if we want to solve for e to the x cosine x, notice since these integrals are the same, you can actually combine them like terms by adding the integral e to the x cosine x dx to both sides of the equation. Now let's see what that leaves us with. Well, just like other like terms, an integral of e to the x cosine dx plus another integral of e to the x cosine x would be 2 times the integral of e to the x cosine x. And then all that's going to be left on this side is e to the x sine x plus e to the x cosine x. And the last step to solve for this integral is just divide by 2. So that'll give us the integral we're looking for, e to the x cosine x equals e to the x sine x plus e to the x cosine x divided by 2. And of course, with any indefinite integral, you always need an unknown constant plus c. So anytime you end up in a loop like that, where you get back to the original integral, and use integration by parts, this is the strategy you can use to help you solve for that integral. Finally, let's take a look at a definite integral. So far, all the ones we've looked at have been indefinite. This one is definite because it's an integral from 0 to 1, has lower and upper limits. So we can start off in the same way. Figure out what to set f of x equal to, and g prime of x. In this case, though, the only thing in there is arctangent, which is also written tangent with the inverse of tangent. So just think, is it easier to integrate that or take the derivative? Well, if it's easy to integrate it, we would not even need integration by parts. So that's your clue. You want to set that equal to f of x, so we can take the derivative. And then since that's the only thing left for g prime of x to equal is, again, just 1. So then when we take the derivative, f prime of x, the derivative of arctangent, remember it's 1 over 1 plus x squared. And when you find the antiderivative of 1, g of x will just equal x. So when we work out what this equals, I get f of x, which is arctangent x, times g of x, which is x, minus the integral of f prime of x, 1 over 1 plus x squared, times g of x, which is x, dx. Difference is, though, this is a definite integral, so there's a couple things that happen. This will go from 0 to 1 there, carry those lower and upper limits over. And since we've already integrated part of it, but not the other part, it's the definite integral, so we've already integrated that part from 0 to 1. We can just start plugging into that part. So let's just clean this up a little bit here. So we'll have x, arctangent of x, from 0 to 1. And then over here, in order to integrate that, I'll get the integral from 0 to 1 of x over 1 plus x squared dx. So to integrate this one requires using a technique I learned earlier, which is use substitution. So in this case, what you'd say u equals 2 is the entire denominator. You can see that's going to work because the derivative of that's going to be 2x, which will help us cancel out that x eventually up there. So remember, with a definite interval, when you use u substitution, you also need to convert your lower and upper limits. So let's go ahead and do that so we don't forget. So if we substitute in 1 for x, that's 1 plus 1 squared, gives you 2. If we substitute in 0 for x, you get 1 plus 0, which is 1. And then we'll have x over u. And then to get rid of the dx, we have to take the derivative of this. So du dx, the derivative of 1 plus x squared would be 2x. So if you multiply both sides by dx and divide by 2x, you get dx equals du over 2x. So let's simplify this. Now you can see that x's would reduce out. You can pull out the 1/2 along with the negative, so we'll have negative 1/2 on the outside. And we go from 1 to 2. And all that's left inside there is 1 over u. So now that one's all set to integrate. So we have negative 1/2 out in front. When you integrate 1 over u, gives you the natural log absolute value of u. Value from 1 to 2. And then you would substitute those in along with, let's go ahead and plug these in as well. So on this one, if you plug in 1, we'll get 1 times the arctangent of 1. So, yeah. And then minus 0 times the arctangent of 0. Remember here we've got a negative 1/2. And we substitute in the upper limit. 2, that becomes the natural log of 2, the absolute value doesn't affect the 2, minus, substitute in 1, the natural log of 1. And so we just have to simplify this. Well, here with arctangent of 1, remember tangent is the opposite over the adjacent. Since we're looking for 1, we look in the first quadrant here, on our unit circle. And the opposite is 1 and the adjacent is 1. Should be able to recognize it's a 45, 45, 90 triangle, which in radians is pi over 4. So the arctangent of 1 is pi over 4. The 0 wipes that out. Arctangent of 0 is also 0, so those are gone. And minus 1/2 natural log of 1, let's say e to what exponents 1 is just 0. So that's gone, so all that's left is 1/2 times the natural log of 2. And you could move that 1/2 up to the exponent, make it 2 to the 1/2 with the square root of 2, or you could just leave it like that. So that would be our answer for the definite interval. And that concludes the notes for AP Calculus on the topic of integration by parts.